Hello, y'all. Welcome to lesson 48, structure 2.2.10 of my DP chemistry curriculum. We're talking about chromatography. It's a technique used to separate the components of a mixture based on relative attractions involving intermolecular forces to mobile and stationary phases. So we'll explain, calculate, interpret the retardation factor RF of different samples, as well as learn what that is. We'll make knowledge of the use of locating agents in chromatography, even though it is not required, we're still going to do it. And we're not going to talk about gas chromatograph or high performance liquid chromatograph, so we're just going to kind of ignore those techniques. So, as we get into chromatography, let's really quick do an introduction on dyes versus pigments because we're going to use dyes and pigments within chromatography quite often, doing both synthetic and natural experiments. So, dyes, about the main points about them is that dyes are usually synthetic, meaning they're made in a lab. In addition, they're usually very small molecules, and they're also usually polar molecules. That way we can like incorporate them with water, our uh, main solvent we use for pretty much everything. Because they're small and polar, they dissolve very readily with water. Meanwhile, pigments are usually natural. So think about the colors in nature, like carrots and corn coming in different varieties of colors, flowers, all that stuff. Those are usually pigments. So in addition to being natural, they're usually very large molecules. These biomolecules are very, very large. And furthermore, they're very much non-polar most of the time. They may have polar ends, but much like we talked about in the last lesson, they can be overall non-polar even with some polar parts to them. So we're going to use chromatography to separate different dyes, separate pigments, and we'll figure out which techniques we use. So this is where we come into what chromatography really is. We already learned that it's a separation technique, meaning it separates parts of a mixture. We can tech spelled that wrong. Technique. So we can use it to separate different parts of a mixture. In this lesson, we're going to mostly talk about paper chromatography. Uh, we will we will often talk about thin layer, but not right now. So thin layer will be later. So we're mostly talking about paper chromatography. We've already learned back from like lesson 1 or 2 that this is a qualitative process, meaning we're not going to get numerical data that will tell us how much of something's in a sample. We still can get some numerical data, which will be the retardation factor we'll learn about, but it doesn't actually lead to knowing how much of something there is. It just tells us what is and isn't there. Furthermore, it involves two phases working together. So we have our mobile phase and our stationary phase. Now, these are generally words you don't necessarily use in a lab often, so it's a little confusing when you see mobile and stationary phase. These aren't like this happens first and this happens second. These are parts of the actual setup. Our mobile phase is what we refer to as our solvent. So our solvent is the mobile phase. The stationary phase is the paper, the filter paper that we use. And within this, the mixture is attracted to one more than the other. The mixture will be attracted to one phase more than the other. And this is how it separates out. So this is going to be based on IMFs. And usually our phases are opposite polarity. So mobile phase is usually polar, while stationary phase is usually non-polar, but we can switch it. So when we look at a chromatography setup, so let's look up setup and we'll actually draw this out. So generally you have some form of beaker with some liquid in the beaker. This liquid is usually our solvent, not usually, it is our solvent. And this liquid is what we refer to as our mobile phase as it moves. So it's going to be moving up our chromatography paper. Our chromatography paper will be dipped in so that the tip is just in, and usually we will set this up so it's attached above the edge of the beaker. And on that, we usually draw a line as our starting point, and that line is usually in pencil. The filter paper is what we refer to as our stationary phase. It doesn't move. This is where the names come from. So it's stationary because this paper stays in the same place the whole time and the liquid will move up the paper. Then we have our mixture. Oops, I want to do that with a highlighter. So this will be our mixture or substance we're analyzing. And as we get our liquid, our mobile phase, to move up the paper, it will draw up parts of the mixture. So we'll get some spots to appear. Now, there's a couple key points here, and I'm going to use blue because this involves the stationary phase. This distance right here is what we call our solvent front. It's how far it moves. This paper we get afterwards with all our spots, and let's use red for this, we will call this our chromatogram. So that is what we analyze after. So we're going to analyze our chromatogram. And we'll notice that we have different pigments or dyes, depending on what we're doing, moving different amounts. And meanwhile, our solvent moves all the way up, and that's our solvent front. All right. One quick thing that the IB gets really picky about is this line you draw should be drawn with pencil. Mostly because pencil versus pen, which is made of dyes and pigments, pencil won't move. Pencil will not interact with our solvent at all. So the key here is that our mixture or components of the mixture travel up the stationary phase more if they are more attracted to mobile phase. So if we have two pigments in this example, this pigment is much more like our mobile phase than this pigment. So basically, if our mobile phase is polar, so if, for example, this since it's polar, this is also polar, and this may be less polar. It's not nonpolar because it moved, but it's definitely less polar. So let's go over what we talk about with qualitative data. A couple things that help us know this is qualitative. The spots indicate purity. They don't say how pure, but for example, one spot would be one substance, would be pure. Two spots would indicate a mixture. But we know this is qualitative because it doesn't say how much percentages. So it doesn't say 30% one thing, 70% another thing. Two spots just indicates a mixture. So we could go 3 or 4, 3, whatever. Anyways, furthermore, we can compare a chromatogram against a known reference. So a good example of this is if we have a couple chromatograms. Or actually, better yet, we could do this all on one page. So we've got our starting line, and we say this is sample 1, this is sample 2 that we know, and this is unknown. And we get our nice chromatogram that we'll start with our bases. This one goes up here, this one goes up here, and our unknown goes up here. Well, we know that our unknown is actually number 1 because it reaches the same point. However, it won't really tell us if it's very concentrated number 1 or very not concentrated number 1. Furthermore, if we threw a number 3 in here that starts here, oops, let's say we consistent with the colors, and 3 goes here and our unknown is here and here, we know unknown is now number 1 and 3, but again, we don't know the percentage. So it could be any percent and any percent. So once again, this is qualitative. It'll tell us what it is, but it won't tell us how much. It won't give us an actual value of how much it is. So we still can get some numerical data. We have this thing called the retardation factor. And that we use the symbol R lower subscript f. Now, this is basically a way that tells us the distance the mixture travels in reference to solvent front. What this does is it helps us work with different mixtures at different times, and I'll indicate why that's important in just a moment after we learn about how to calculate it, RF. So the actual value for RF is the distance traveled by substance divided by the distance traveled by mobile phase. So this is the equation that I think is in your data booklet, but here's what I'll talk about why it's important to have this and also why, once again, it's not going to be a quantitative data. This will be qualitative. But the important thing is if you look at a couple pieces of chromatography paper and we look at these pieces that have been in a substance for different amounts of time. The longer you keep it in the solution, the higher up our solvent's going to travel. So this may be like 1 minute, this may be 2 minutes, and this may be 3 minutes. And so if you're just comparing against an unknown, it's often hard if you don't know how long that unknown went in. But the key here is the actual amount of movement will be proportional. So even though they've all moved a different amount, retention factor doesn't matter about the time. This will still be 0.5, this will still be 0.5, and this will, I lost my point. This one will also be 0.5. So what I'm saying is because it's a proportion of the movement, having your chromatograph be in the solution for longer doesn't actually affect the value for retention factor. So we could have our 3 knowns. So we'll say known 1, or we'll just do 2 knowns, known 2. And maybe these have been in for 30 seconds. So known 1 and known 2, we have different retention factors. And it looks like the solvent still moved the same distance, but it really didn't. Because we wouldn't see from known 1, our retention factor would be 0.5, but our retention factor for known 2 would maybe be 0.1. And so we know known one is our unknown sample here. So this is some stuff that you're going to have to get used to doing and analyzing. You will need to know how to read a chromatogram. And so I hope this section helps. Ooh, one last thing before the end of it. So one big difference between thin layer chromatography and paper chromatography is we use paper in paper chromatography, but in thin layer chromatography, the main difference here is that our stationary phase in TLC, thin layer chromatography, is usually silica gel. Silica gel. Uh, and this is in thin layer. We're going to talk about it a lot more in a later section, but as far as this section goes, that's all you need to know about thin layer chromatography. All right. So with that all said, I hope this helps and have a great day.